All right, hello. I want to share a presentation with you today called Matter and Change 2. It's a second presentation about matter and change. We will definitely get into chemical properties today and chemical change. We'll talk about mixtures and a variety of other things and a little bit of review. Let's begin. Here's how I want to begin. I want to begin with a point that I made in the first lecture, and that is, you heard me say, what really matters to matter? I want to start with sort of a main point. And the main point that I want to make right at the beginning is, obviously, what you're made of, what you're made of, and the association that you enter into, and obviously I'm talking about bonding types, obviously it's going to have an impact on the state of matter that you are. So, here we go. We have a single atom in a pure substance like gold. Here we have an ionic bond between sodium, a metal, and a non-metal, and we have a crystalline solid that we call salt. Here we have a hydrogen and an oxygen. We have two non-metals joined together in a covalent, even though this is going to end up being a polar covalent bond. And what do we get out of that? We get a liquid. All right, what is the point that I'm trying to make? The point that I'm trying to make is, sometimes we do talk about substances made out of just single elements, but a lot of times we're talking about molecules. We're talking about compounds. We're talking about atoms that have some type of a bonding association. And depending upon what you are and how you're put together, obviously that matters, to matter. All right, so what you're made of and how you're put together obviously is going to matter, okay? All right, as another little tidbit of review, remember one of the most famous liquids to man, water, which could be in a solid state or a liquid state or a gaseous state, water vapor. And notice how you have a geometrical arrangement of water molecules in a solid like ice. Here you would have water molecules that are free to move around one another because water can flow, but that would be a liquid. Here you would have water molecules that have enough kinetic energy to literally separate from one another and go out into the atmosphere, but yet that would be a gas. But yet, at the end of the day, this is just such an awesome fluid. It's such an awesome, I should not say fluid, such an awesome compound, because it can exist as a solid, liquid, or gas. So 3 states of matter. But at the end of the day, it's still a water molecule. All right, and that's fascinating. And we start thinking about these different states of matter and what they're made of and how they're put together and the attributes that they have. And we just find that it becomes a very, very fascinating topic, okay? Remember the difference between a molecule and a compound. A molecule is for instance, is diatomic oxygen, but a molecule can be 2 atoms of the same type bonded together. This can also be a molecule. But at the end of the definition, this is a compound and this is not. A compound would have to be made up of at least 2 different kinds of atoms. And even though you have 3 atoms here, you only really have 2 different kinds of atoms, carbon and oxygen. Carbon dioxide that you exhale, oxygen that you inhale, 2 gases extremely important to man, extremely important to plants. But while both could be a molecule, this would be kind of our definition of compound. And we tend to throw those words out a lot, molecule and compound. So I think it behooves us to know sort of what that means, okay? Obviously, these are both gases. So if you're looking at the state of matter here, you're looking at a gas. All right, let's start talking today a little bit about chemical properties of matter, okay? And, the one that kind of resonates or stands out to me probably here is flammability. And I'm going to skip ahead for just a second because, it's not uncommon for you to buy aerosol cans, especially, where you might see a caution, extremely flammable. Well, that is a chemical property of the item that is in that canister. All right, so that would be a chemical property. And we'll continue to talk about that, okay? I really like this table, and I would encourage you to look at this table in your notes, because while I'm not going to really talk about physical properties today, you should look and understand physical properties. Especially you want to remember that a change in state is a physical property, and that's exactly one of the reasons why I wanted you to see this slide earlier. This is, it's still water molecules, right? Okay, so remember that a change in state particularly is physical, but here are some other physical properties. But today we want to focus on things like reactivity, things like toxicity, corrosion, radioactivity, flammability, pH, oxidation. A chemical property is a characteristic of a substance that describes its ability to change into different substances. So these, are the ability to change. So a chemical property is the ability to undergo a specific chemical change. Listen, this car did not roll off of the manufacturing facility floor rusting, all right? This happened over years of exposure to the elements. This happened, this is a car that's sitting in a junkyard somewhere or a farmer's field somewhere. And so this is a chemical change, but obviously it did not roll off of the manufacturing floor rusting. So a chemical property can only be observed when and if they happen. All right, so if you can rust, that would be a chemical change, but you're not necessarily rusting until you rust, until you start that process. So I know that sounds kind of silly, but you got to think about this. It's true. This flammability, there are who knows how many people that spray their hair with hairspray every day and they suffer no calamity. There's nothing that happens from that. But what if that hairspray were to come into contact with a spark or a flame? Then it would be flammable. So you got to remember that chemical properties, can only be observed when and if they happen. Now, on the other hand, if I have a white piece of paper, then I've got a white piece of paper. I can readily observe that. If I take this piece of paper and I crumple it up, then I can readily observe that, but yet I'm not really changing the composition of the paper. So a chemical change, and I'm going to get a little ahead here, but a chemical change, you're going to have something different at the end, but you're not going to have that change until the change occurs. So a chemical property says that you have the ability to do something, but you don't really have that taking place until it takes place. Okay, so let's continue. So like for instance, if I take an Alka-Seltzer and throw it in water, intuitively you're watching this process take place in all these bubbles, and you're watching carbon dioxide gas escape into the atmosphere, and you're saying, wow, there must be some kind of change going on there. Yes, so is it a chemical or is it a physical change? Well, let's read this together. Chemical reactions occur when bonds within molecules are broken or formed. There are several things that signify that a chemical reaction took place. These include a change in color, the production of a gas or solid, and of course, a change in chemical composition. And that's the big deal, a change in chemical composition. The starting chemicals before a reaction are called the reactants, and the chemicals that are produced are called the products. Okay? So if you have a barometer for measuring something, so what's your barometer for measuring it? Well, if what you have at the end is what you had at the beginning, it's physical. A physical change. If what you have at the end is not what you had at the beginning, in other words, different, it's still going to be the same elements and atoms. But if it is different, then it's going to be a chemical change. A physical property is going to be something that could possibly change, and a chemical property will signify the ability to change. Okay? All right. So what is the key factor? All right. And once again, remember, today we're focusing on chemical change. So what's the key factor? Well, I made something up here. It's just a made up equation. All right. We have xy plus z equals xz plus y. Now, you need to make note of the fact, do I have an X here? Yes. Do I have an X here? Yes. Do I have a Z here? Yes. Do I have a Z here? Yes. Do I have a Y? Yes. Do I have a Y? Yes. Why am I telling you that? Because we are not going to labor under the impression that we can turn lead into gold. I wish we could. We're not going to do that. Whatever we have on in our reactants is going to be the same elements that we're going to have in our products. We don't have the ability to create new matter or to change one atom into another atom. So in a sense, what we have here is always going to be what we have here. But we're looking at the way they're put together. We're looking at our reactants versus our products. And what do we see? Well, if we just look at this basic equation, we see that X joins with Z and Y is now sit by itself, maybe liberated. What do you mean liberated? Well, maybe Y is a gas. I mean, what is going on here? You know that this gas is going to come up and it's going to come out of this container and escape into the atmosphere. So maybe that's what's going on here. Maybe this is a gas, and maybe it isn't. At this point, to be honest, I don't really care. What do I care about? I care that my reactants are not the same as my products. But whatever I have at the beginning also has to be reflected at the end. This is also shown here when I label my reactants and make sure that I pay particular attention, once again, to my products. But what's a big deal? The law of conservation of matter, or the law of conservation of mass. Can you imagine if we lived in a world where we could destroy matter? I mean, just poof, it doesn't exist anymore. It would beg the question, how long until we run out? And what if we really could change lead into gold? I mean, wow, that would be kind of cool, right? But we don't have that ability. So on Earth, we have what is called, when these reactions take place, we have what is called conservation. So in other words, whatever I have here, I'm going to have here. Now we may alter its form or it's the way whatever's put together, that I want to say composition. We may liberate a gas where there wasn't a gas before, but the point is, whatever we have here will be reflected here in terms of the atoms and the elements. But what we have here in our products, remember, these are our reactants and these are our products. So whatever we have in our products, and if it's a chemical change, it's going to be different. And that's going to be the key hallmark feature of a chemical change. We're not going to have at the end what we had at the beginning, but we have to conserve the matter. The matter has to be conserved. It doesn't go poofy and disappear into nowhere land. Okay, that doesn't happen. All right. So make your biology teachers proud, and let's use a real life example. Let's use the example of photosynthesis. So we bring in 6 molecules of carbon dioxide, 6 molecules of water, and in the presence of chlorophyll, light, probably energy, enzymes, plant, leaves, all the above, the plant will create 1 molecule of sugar and 6 molecules of diatomic oxygen. Now, by the way, that's a gas, as you know. So that gas will escape into the atmosphere, which is a good thing for us. The sugar will be left behind in the plant, and then you will either consume the plant or you will consume something that consumed a plant. Okay? And what gets stored in that? Well, obviously energy from the sun. But here we go. What do I need for you to see? Well, I need for you to see that what we really want is we want a balanced chemical equation. So in other words, we want to have whatever we have here in whatever proportion that we have, we also need to have here. However, it's pretty darned obvious that we had carbon dioxide, which is a gas, and we had water, which is a liquid. We end up producing a sugar and giving off another gas, which we did not have present over here. So while we are conserving matter, we are creating something different out of the same materials. So this is a definite chemical change. Okay? It's a chemical change. So in a chemical change, the properties of a material change and the composition of the material changes. Okay? The properties of a material change and the composition of the material changes. But the matter is conserved. So once again, you go back to a car that's sitting out in some junkyard somewhere rusting. I mean, if you look closely enough at this picture, there are holes. There's no longer metal there. That metal is gone. So obviously, if that metal is gone, once again, it didn't roll off the assembly floor looking like that. So it obviously has to be a chemical change because you don't even have the metal there anymore. So that's obviously a chemical change. Now, if metal has the ability to rust, well, that's one thing, but you don't have rust until you have rust. Okay? All right, let's review quickly. 3 states of matter, actually 4. We have a solid, liquid, gas, and plasma. And you're like, well, I know that, Mr. Day. Well, that's good. Just remember that the geometrical arrangement or the arrangement of the atoms or the kinetic energy involved, there's going to be differences. Well, you would expect that because they are different states of matter with different characteristics. So that's exactly what you would expect. And what matters to matter? Well, what you're made of and how you're put together obviously matters, okay? Don't forget that you can sometimes skip a state. So when you have sublimation, with dry ice or sometimes in atmospheric conditions when you go straight from a vapor, in that case the air would probably be like this. You go straight from a gas to probably a solid like ice. But if you skip a state, that is called sublimation. All right, let's talk about mixtures. All right, if we have a substance, or if we have, let's put it like this. Let's say I have a liquid. Let's say I have tap water that comes, municipal water coming straight from the tap. Or let's say that I have distilled water, which I buy in gallon jugs at the grocery that has been run through the process of distillation. Well, one of them is a pure substance. This is just pure water. This is just a bunch of water molecules, but it's a pure substance. Well, what about tap water on the other hand? I don't see anything in it, Mr. Day. It looks just the same as the distilled water. Well, come on. It's went through a purification facility. It's going to have some chlorine in it. It's going to have fluorine because we add fluorine into our municipal water supplies because we've learned that it's good for our teeth. So this is going to be a mixture. Now, because you can't really see it, then it's pretty much what we call a homogeneous mixture. It's very evenly distributed, very uniform in composition, but it's still a mixture. Well, this mixture is a heck of a lot easier to see. You can see the individual jelly beans. You can tell they're a different color. I mean, this is easy to see. You understand the idea of a mixture, but sometimes it's not so easy to see. Like for instance, if we took some sugar and we put it in water and we mixed it up, water is a fantastic solvent. So it would dissolve the sugar and you probably wouldn't even know until you took a drink of the water and it tasted very sweet. So once again, that would give us a very homogeneous solution, okay? But it's still a solution. It's still a mixture. In this case, it's a very homogeneous, very uniform distribution mixture, okay? Let's read about that. A homogeneous mixture of 2 or more substances in relative amounts that can be varied continuously up to what is called the limit of solubility. Here's what we're saying. There's going to be a point where you can't put any more sugar in the water, but until you reach that point, you can just continue to add sugar and it will mix very evenly. But at some point, you're not going to be able to keep adding sugar. But at this point in this picture, there's been no problem because we have not reached the limit of solubility. So we have a very homogeneous mixture. The term solution is commonly applied to the liquid state of matter, and that's what we've been talking about so far. However, solutions of gases and solids are possible, and that's interesting because a lot of people probably don't know that. Okay, for instance, I'll just skip ahead for a minute. Stainless steel. You mean there are examples of solids that are mixtures, homogeneous mixtures? Yes, and stainless steel would be an example of a solid, and we'll come back to that in just a second. All right, so let's just think about what we're considering here. So we're considering mixtures. Well, what if I just had a pure substance, Mr. Dave? Could I have just a pure element? Yeah, once again, I could just have pure gold, but that's not a mixture. Okay, that's just one atom of one element. Well, what if I had pure water? What if I just had a bunch of water molecules? What if I had, every one of these was a water compound, right? H2O. Okay, fine, but that's not a mixture. Okay, those are pure substances. Now, what if I were to mix something in with my water, such as sugar? Then that's fine. And if it's an even distribution like this, then it's going to be what we call homogeneous. But what if I had a mixture that was not even and uniform and distributed evenly? Then we would call that heterogeneous. Okay? And you also know, you've heard these prefixes used before. You know that homo means same and hetero means different. So this would be a very uneven mixture. But so far, we've pretty much just been talking about homogeneous mixtures. Okay? So a homogeneous mixture, one more time, would be a very even distribution. And that's all, this is nothing specific. This is just a visual aid to help you understand homogeneous. Okay? Now, what if I were to take like vinegar or water even and pour in some oil or some cooking oil? What would I get? Well, you've done this before or seen it done before, and you know that because of, and this is all really due to density, but obviously we would have two different layers here. Okay, we're not going to consider this a homogeneous mixture. This is not the definition of uniform and definite composition. My friends, this is going to be a heterogeneous mixture. Now, it's not the only example of a heterogeneous mixture, but that's what it's going to give us. It's going to give us a heterogeneous mixture. Okay? Now, most of the time when we're using this term solution, we're talking about homogeneous mixtures. Okay? And many of our solutions are liquids, but once again, some could be gases, so there could be mixtures of gases, and in fact there are. The atmosphere is certainly not all oxygen. In fact, the majority of the atmosphere is not oxygen. Okay? And there are some examples of solids. So once again, stainless steel. Stainless steel is a homogeneous solution of what? Iron, chromium, and nickel. So there's the different states of matter, solid, liquid, gas. So you can have solid, liquid, and gas homogeneous solutions. Okay? Now what if we're heterogeneous? Because we haven't really talked as much about that. Well, if we're heterogeneous, then obviously we do not have this uniform and definite composition that we have here. So this is heterogeneous right here. So, I don't know, maybe we mix together some salt and pepper. Maybe, back when you were a kid and you were making mud pies and you were putting dirt in water, and then it looked like it was a nice solution, and then you came back the next day and all the dirt had settled to the bottom. I don't know. I mean, we could come up with different examples, but a heterogeneous mixture is not going to have a uniform and definite composition. And so here's what we say. We say that from the standpoint of looking at this, we say that a homogeneous mixture is what we call a single phase because it is so evenly distributed. Whereas in this case, we have a very uneven distribution. So in this case, we would have two phases. This would be a two-phase. Now, what if we had more than two items in there? Then I suppose we could have more than a two-phase. But in this case, we're looking at a two-phase. Okay, so heterogeneous, homogeneous. Okay? Now I'm going to close with sort of an idea. You can separate mixtures. It might be as simple as something, very physical that you could do in like a filtration, like just a simple filtering. But going back to when we mentioned distilled water a while ago, and and distilled water is very cool because we use a physical property. A physical property, remember, change in state is a physical property. Well, it's a physical change, but physical properties are things like boiling point, melting point. So what we do is we take our solution, we bring it to the boiling point of water. We allow the water vapor to rise, we cool the water vapor, which allows it to condense, and then we catch it over here. So what are we doing? We're catching pure water, and we're leaving the impurities behind, and then we'll get rid of this, and we'll take this, and we'll have nothing but pure water. This is a simple distillation apparatus. So obviously it involves heat. Now what's the point? The point is that there are mechanisms by which we can separate mixtures. And this would be an example of one. But it's kind of cool because it's actually using a physical property to carry out, and to get a pure substance. And the pure substance in this case would just be water. Now, before we close, so see the big picture, all right? What matters to matter? Well, what you're made of and how you're put together, obviously. What else? Well, there's 3 states of matter that were very common to us on Earth, 4 states total, all right? What else do we want to know? We want to know that we have physical properties and physical changes, but we also have chemical properties and chemical changes. Well, what is a chemical change? Well, at the end, you better not have what you had at the beginning in the same form or same composition or same ratio, okay? Otherwise, you're not a chemical change. Can we have mixtures? Yes, we can have homogeneous and heterogeneous mixtures, and we need to understand some of their similarities and differences, okay? But at the end of the day, we want to understand that we can have chemical change and physical change, so we're going to have chemical properties and physical properties, and they aren't going to be the same.